Alright, we're going to react to every type of black hole. Okay, let's watch. And if I hear something interesting, I'll come back and I'll talk about it.
Some black holes weigh no more than a single star. Others are so immense they anchor entire galaxies in place. And then there are the most mysterious kinds, objects that may exist only in theory but defy everything we think we know about reality. Today, we'll climb through all 5 levels of black holes, from the smallest stellar corpses to the most mind-bending possibilities in the universe. But first, what exactly is a black hole? At its simplest, a black hole is a region of space where gravity has become so overwhelming that nothing, not even light itself, can escape. Imagine compressing the mass of our sun into a sphere just a few kilometers wide. The resulting pull would be so strong that it bends the very fabric of space and time around it, creating a cosmic trapdoor with no return. This boundary is known as the event horizon, the point beyond which escape is impossible. Anything that crosses it, matter, energy, even information, becomes part of the black hole forever. And yet, for all their terrifying reputation, black holes are not cosmic vacuums roaming through space, hunting stars and planets. They are instead the natural outcome of physics pushed to its absolute extremes. When massive stars collapse under their own gravity, when matter piles up past certain thresholds, or when the universe bends to quantum rules we still struggle to understand, black holes emerge as the inevitable conclusion. But here's the real mystery: not all black holes are the same. Some form from dying stars only a few times heavier than our sun. Others grow into monsters millions or even billions of times that size. And then there are black holes predicted by equations but never yet seen. Objects that challenge the very boundary between science and speculation. That is where our journey begins. Over the next chapters, we'll climb step by step through the hierarchy of black holes. From stellar corpses to quantum enigmas, this is the full scale of the universe's strangest and most powerful objects. So buckle in as the journey into the darkness begins. The story of black holes begins with stars, the brilliant furnaces that light up galaxies. But like all things in the universe, stars have lifespans. When the most massive ones reach their end, they don't fade quietly, they collapse, triggering explosions so powerful they outshine entire galaxies for a brief moment. What remains after this chaos can be something extraordinary: a stellar black hole. Not every star qualifies for this dramatic fate. Our own sun, for example, is far too small. It will die more gently, becoming a white dwarf. To create a stellar black hole, you need a giant, usually a star at least 20 times heavier than the sun. Once such a star exhausts its nuclear fuel, its core caves in on itself. Gravity overwhelms every other force, crushing matter to unimaginable density. The result is an object that weighs between 3 and 100 solar masses, yet fits into a sphere no larger than a single city. Pause for a moment and picture that. A black hole just a few kilometers wide but with the mass of dozens of suns. If Earth were to replace its core with such an object, our entire planet and everything on it would be swallowed instantly. The scale is so extreme that ordinary comparisons barely capture it. Imagine compressing the Himalayas into the size of a pebble, or the population of the world into a single grain of sand. That is the kind of density we are talking about. But how do we find something that, by definition, gives off no light? The answer lies in their surroundings. A black hole may be invisible, but its presence is revealed by the havoc it causes nearby. When paired with a companion star, it can steal gas from its partner. That gas doesn't fall straight in. It swirls around first, forming a spinning disk that heats up to millions of degrees. This accretion disk glows in X-rays, producing signals powerful enough to reach Earth. By scanning the skies with X-ray telescopes, astronomers can pick out these cosmic beacons. We can also detect stellar black holes through gravity itself. If a star appears to orbit an unseen companion and that companion's mass is far too great to be anything ordinary, the explanation is clear: a black hole must be there. And thanks to instruments like LIGO and Virgo, we now have another tool: listening for the faint ripples ripples in space-time created when two black holes collide and merge. These gravitational waves are like cosmic drumbeats telling us where these hidden objects are. Perhaps the most famous example is Cygnus X1, discovered in the 1960s. Located about 6,000 light-years away, it was one of the first black holes ever confirmed. At its heart lies a black hole around 21 times the mass of the Sun, locked in orbit with a massive blue star. The system's X-ray emissions were so strong they couldn't be ignored, and over decades of study, scientists proved beyond doubt that Cygnus X1 was indeed a black hole. The discovery was so significant that it even sparked a playful bet. Stephen Hawking once wagered that Cygnus X1 would turn out not to be a black hole. When the evidence piled up, he conceded, admitting that gravity had once again proven itself the strongest force in the universe. Astronomers now believe there could be millions of stellar black holes scattered across our galaxy. Most lie dormant, not feeding on nearby stars, and so remain invisible to us. They drift through the Milky Way silently like cosmic ghosts, undetectable unless we stumble upon the clues they leave behind. Some may wander alone forever, while others grow by consuming stars or merging with fellow black holes. Stellar black holes are more than just remnants of dead stars. They are nature's first demonstration of what happens when matter is pushed beyond all known limits. They show us gravity's raw power, unchecked and absolute. In short, these black holes are cosmic paradoxes. City-sized objects holding the weight of suns, invisible traps that we can only find through their shadows. They are where the hierarchy of black holes truly begins, and the first step into a universe stranger than anything we experience on Earth. If stellar black holes are the small seeds of the black hole family, and supermassive ones are the giants ruling galaxies, then what lies in between? Logic suggests there must be middleweights, objects heavier than stellar black holes, but not nearly as monstrous as the supermassive kind. These are what astronomers call intermediate black holes, and they represent one of the most puzzling mysteries in modern astrophysics. On paper they seem obvious. A stellar black hole can weigh a few dozen suns, while a supermassive black hole can weigh millions or billions. Surely, somewhere in between there must be black holes weighing hundreds or thousands of suns, and yet, despite decades of searching, they remain some of the hardest objects to pin down. What makes them so special is not just their size, but what they could reveal. They may be the missing link in black hole evolution. The step that explains how small stellar remnants could grow into the behemoths at the centers of galaxies. Without intermediate black holes, it's difficult to understand how the universe built its largest structures. So what do we know? Estimates suggest intermediate black holes should weigh anywhere from a few hundred to perhaps 100,000 solar masses. That's small compared to the titans at galaxy cores, but unimaginably huge compared to their stellar cousins. Imagine compressing the entire mass of a star cluster into something no bigger than a moon. That's the territory we're talking about. The problem is that finding them is like chasing shadows. Unlike supermassive black holes, which light up their surroundings as quasars, intermediate black holes are faint, quiet, and often hidden. They don't feed on vast amounts of matter, and they don't always sit in convenient places where we can spot them. Instead, scientists have to hunt for subtle hints of their presence. One promising clue comes from dense star clusters, regions where hundreds of thousands of stars are packed tightly together. If an unusually heavy object lurks at the center, it can tug on the motions of the surrounding stars. By mapping those orbits, astronomers can sometimes infer that a hidden black hole is there. A candidate like this was found in the globular cluster 47 Tucanae, where the movements of stars suggest something with thousands of solar masses might be hiding. Another clue comes from dwarf galaxies, small galaxies on the outskirts of larger ones. Some of these faint systems appear to host black holes that are neither stellar nor supermassive, but something in between. One striking case is a galaxy called HLX1, about 290 million light-years away. Astronomers believe it contains a black hole around 20,000 times the mass of the Sun, an almost perfect example of the intermediate category. We've also caught fleeting glimpses of them through X-ray flashes. Occasionally, when an intermediate black hole consumes a passing star, the resulting burst of energy can be seen across space. These rare events may provide some of the strongest evidence that these hidden giants are out there. And yet, for every candidate we find, more questions emerge. Why are intermediate black holes so rare, or at least so hard to see? Are they simply too quiet, existing in places where they rarely feed? Or is nature itself reluctant to form them, skipping straight from stellar black holes to supermassive ones by some unknown process? This is what makes them so tantalizing. Intermediate black holes could hold the key to the growth of galaxies, but they remain elusive, like missing pages from the story of the universe. Some scientists believe that as our instruments improve, especially with the next generation of gravitational wave detectors, we may finally catch them in the act of merging, sending out signals that confirm their existence beyond any doubt. For now though, they remain an enigma, neither small enough to be common nor large enough to stand out. Intermediate black holes sit in a shadowy middle ground. They are the quiet giants we know must exist, but can rarely see. They remind us that the universe still keeps secrets, even about its most powerful objects, and as we search for them in clusters, galaxies, and ripples in space-time, we may discover not just where they are, but how every black hole in the cosmos came to be. If stellar black holes are the seeds of collapse, then supermassive black holes are the towering trees of the cosmic forest. These are the true giants of the universe, black holes so immense that their masses reach millions or even billions of suns. And unlike their smaller cousins, these titans don't hide in random corners of space. They sit at the hearts of galaxies, shaping and anchoring the worlds around them. Take our own Milky Way, for example. At its center, 26,000 light years from Earth, lies a monster known as Sagittarius A. This black hole contains about 4 million solar masses, all crushed into a region smaller than the orbit of Mercury. We can't see it directly, but we can trace the orbits of stars whipping around it at breakneck speeds, some completing a full orbit in just a few years. The only explanation for such furious motion is the invisible gravity of a supermassive black hole. And Sagittarius A is modest compared to others. The galaxy M87 hosts a black hole more than 6 billion times the mass of the Sun. In 2019, it became the first black hole ever imaged directly by the Event Horizon Telescope. The iconic picture, a glowing ring of light surrounding a dark shadow, was humanity's first glimpse at the edge of an abyss billions of light years away. To put its scale into perspective, if stellar black holes are city-sized, supermassive black holes are larger than our entire solar system. But the real question is, how did these giants form? Stellar black holes are easy to explain. Stars collapse, gravity takes over, but there is no single star large enough to collapse into something millions of times heavier than the Sun. So where do supermassive black holes come from? One theory is that they began as smaller black holes, which grew over cosmic time by swallowing stars, gas, and even merging with one another. Another idea is that in the early universe, massive clouds of gas collapsed directly into black holes, bypassing the stellar stage entirely. The truth is still uncertain, and solving this mystery may also solve the question of how galaxies themselves formed. Because these black holes are not passive passengers, evidence suggests they play a central role in shaping the galaxies around them. As matter falls in, it can release titanic amounts of energy, powering what we call quasars, brilliant beacons so luminous they can outshine entire galaxies. These quasar outbursts can drive winds strong enough to blow gas out of galaxies, regulating star formation and sculpting their evolution. In this way, supermassive black holes are both destroyers and creators, curbing the birth of new stars, but also helping set the rhythm of galactic life. It's humbling to realize that every large galaxy we've observed seems to have one of these giants at its core. Without them, galaxies as we know them might not even exist. Our own Milky Way's spiral arms, our neighboring Andromeda galaxy, and the distant beacons of the universe are all structured around these invisible anchors. And yet, despite their overwhelming influence, we're only just beginning to study them properly. The Event Horizon Telescope has now revealed not only M87 but also Sagittarius A, offering us direct evidence of the shadows they cast on space-time. Future observatories, from space-based X-ray telescopes to more advanced gravitational wave detectors, will continue to lift the veil on their behavior. Supermassive black holes represent nature's grandest scale of collapse. They are the ultimate proof that gravity, given enough time and mass, can create objects beyond imagination. From millions to billions of suns compressed into a single abyss, they stand as the titans of the cosmos. And as we've seen, their influence stretches far beyond their event horizons. They don't just consume the universe, they help shape it. In the story of black holes, these are not simply larger versions of the stellar kind. They are something altogether different, architects of galaxies, engines of quasars, and keepers of the deepest mysteries of cosmic growth. So far, the black holes we've explored have all formed from stars or grown within galaxies. But what if some black holes are far older than any star, older even than galaxies themselves? What if they were born in the first moments after the Big Bang? This is the idea of primordial black holes, hypothetical relics from the dawn of time. Unlike stellar or supermassive black holes, these would not be the result of collapsing stars. Instead, they could have formed when the universe was less than a second old. Back then, everything was hot, dense and chaotic. Tiny fluctuations in the fabric of space-time might have concentrated matter so tightly that gravity crushed it into black holes on the spot. If they exist, primordial black holes could come in a staggering variety of sizes. Some might be no bigger than atoms, with masses measured in grams. Others could rival mountains or even asteroids in weight. Imagine a black hole smaller than a grain of sand, but heavier than Mount Everest. That's the bizarre scale we're dealing with. But why are scientists so interested in these hypothetical objects? The answer lies in one of the universe's greatest unsolved puzzles: dark matter. For decades, astronomers have observed that galaxies rotate in ways that can't be explained by the matter we see. There must be some hidden mass holding everything together, but what it is remains unknown. One possibility is that dark matter is made not of exotic particles, but of countless primordial black holes scattered through the cosmos. If true, that would mean the missing mass of the universe is literally made of invisible black holes drifting silently through space. Some theories even suggest that trillions of them could be passing through our solar system at any given moment, right through Earth itself, without leaving a trace. Their gravity would be so localized and their size so small that we wouldn't even notice. Of course, the mystery runs deeper. If primordial black holes formed in the early universe, they might also explain how supermassive black holes grew so quickly. Observations show that enormous black holes already existed less than 1 billion years after the Big Bang, but stellar black holes should not have had enough time to grow that large. Primordial black holes acting as seeds could have given them a massive head start. So far though, the evidence is thin. We haven't directly observed any primordial black holes. Scientists search for them by looking for their gravitational effects, like tiny distortions in starlight when one passes in front of a distant star, or bursts of radiation that might occur if a small black hole evaporates through Hawking radiation. Each new telescope and experiment gives us another chance to catch one in the act. But for now, they remain ghosts of theory. Still, the possibility is thrilling. If we could prove their existence, primordial black holes would not just solve the riddle of dark matter. They would also connect the smallest scales of quantum physics with the largest scales of cosmology. They would be fossils from the very birth of the universe, carrying secrets from the first instant of creation. Whether they are real or not, the concept itself reshapes our imagination. Black holes, it turns out, may not just be the final stage of stars. They may also be the first structures the universe ever built. And if that's true, then the story of black holes is not just about death and collapse. It's about origins, beginnings, and the raw power of creation itself. When most people think of black holes, they imagine enormous objects, monsters with the mass of stars or even galaxies. But what if black holes could also exist at the tiniest scales imaginable, smaller than an atom itself? This is the strange and highly theoretical idea of quantum black holes. Unlike the black holes formed from collapsing stars or found at galactic centers, quantum black holes belong to a different frontier. They exist in the space where our best scientific theories, Einstein's general relativity and quantum mechanics, overlap and begin to clash. Relativity explains how gravity shapes the universe on cosmic scales, while quantum mechanics governs the unpredictable world of subatomic particles. Normally, these two frameworks stay in their own lanes, but if matter is compressed down to unimaginably small scales, both sets of laws apply, and neither is fully adequate. This is where the concept of Planck scale black holes comes in. The Planck length, around 10 to the negative 35th meters, is the smallest meaningful unit of space according to physics. A black hole of that scale would be almost inconceivably tiny, far smaller than a proton, yet still carry immense density. In theory, such an object would represent the ultimate meeting point of gravity and quantum physics. But there's a catch. Tiny black holes don't last. Thanks to Stephen Hawking's famous insight, we now believe that black holes slowly evaporate through a process called Hawking radiation. For stellar or supermassive black holes, that evaporation takes longer than the age of the universe itself. But a black hole as small as a particle would evaporate in the blink of an eye, releasing its energy almost instantly before vanishing completely. Could these miniature black holes actually exist? Some scientists have speculated they might have formed in the violent conditions of the early universe when energy densities were extreme. Others wonder if high-energy collisions, like those produced inside particle accelerators such as the Large Hadron Collider, could briefly create them, though so far no evidence has been found. Even without direct proof, the idea is far from idle speculation. Quantum black holes are a thought experiment that forces physicists to confront one of the deepest mysteries in science: how to unify quantum mechanics with gravity. If such objects could be shown to exist, even fleetingly, they would provide a critical clue toward building a theory of everything, a single framework that explains both the very large and the very small. Quantum black holes may never be directly observed, but their significance lies in what they represent. They are not about devouring stars or shaping galaxies, they are about the edge of knowledge itself, where our current theories fail and new physics must emerge. In their tiny horizons could lie answers to some of the universe's greatest questions. We've climbed through the 5 main levels of black holes, from stellar remnants to quantum mysteries. But the story doesn't end there. Beyond these categories, scientists have proposed other fascinating kinds of black holes, some discovered, others purely speculative. Think of these as the bonus round, where reality and imagination meet. One of the most exciting discoveries in recent years has been that of binary black holes, pairs of black holes locked in an orbital dance around one another. For billions of years they circle closer and closer until finally they collide and merge in a cataclysmic release of energy. When this happens, ripples spread across the fabric of space-time itself. We call these ripples gravitational waves, and they were first detected in 2015 by the LIGO Observatory. That moment confirmed not only Einstein's predictions but also the existence of black hole pairs colliding in distant galaxies. Today, every new detection adds another chapter to the hidden history of these cosmic duets. Then, there's a stranger idea: white holes. If black holes are objects that trap everything, white holes are their hypothetical opposites, objects that nothing can enter and from which matter and energy are only expelled. They've never been observed, and most physicists doubt they exist in nature, but the concept is intriguing. Some theories even imagine that a white hole could be the other end of a black hole, connected by a wormhole through space-time. While this remains firmly in the realm of speculation, it captures the imagination as a playful what if in our cosmic story. These bonus examples remind us that black holes are not just astrophysical objects. They're also powerful thought experiments, testing the limits of theory and observation. From pairs that shake the universe with their mergers to mirror images that may never exist, black holes keep challenging us to stretch both our instruments and our imaginations.
They think that white holes are the end, are the the other end, the other side of a wormhole, the other end of a wormhole. That's actually not a bad theory. And the binary holes making a ripple in space and time. That's cool. What was it though? That white hole. That was a good that was a good video. The outro. Primordial black holes. Supermassive black